So now that we have been introduced to sequences and we know the terminology and some of the key words, we are going to finish off 9.4 by looking at two special sequences. The first is known as an arithmetic sequence, and the way you can tell if a sequence is arithmetic is if the differences between two consecutive terms is the same. What that basically will mean to you looking at a sequence is that as you move from the first term to the second term to the third term, you're going to see the same value being added on. Now, that could be a positive value being added on or a negative value being added on. And so we call that common difference the D value. And you can find it simply by taking a sub 2 minus a sub 1. So we say a sequence is arithmetic if there is a common difference. So let's look at 4 problems here and identify if, yes, it looks like it's arithmetic or not. And if it is arithmetic, then let's identify that common difference, that D value. So in the first problem, again, you can do this one of 2 ways. You can either look from term to term, and sometimes it's really easy, for example, in this one, to see that you are adding 3 as you move from term to term. So yes, this is arithmetic. That common difference is that value of 3. If you couldn't see that, something that you can do is you can take, like I said, the a sub 2 and subtract the a sub 1, and that would give you that common difference. You could do that with any 2 consecutive terms. So I could have taken the 17 and subtracted the 14 and also saw that the difference was 3. So that's how you can see if you have an arithmetic sequence. If you want to hit pause and try the next 3 on your own, and then you can come back and see if you got them right. So in number 2, one of the things I notice is this time the sequence is decreasing. So it's going down. If I can't tell what it's going down by or if it's consistent, then I might just do that subtraction of consecutive terms. 16 minus 23, that's a negative 7. 9 minus 16, that's a negative 7. So you want to make sure that that's consistent for all of the terms. And in this case, now that I see that negative 7, that does seem to be consistent. So in this case, yes, we have another arithmetic sequence. That D value is a negative 7. So there's an example where your D can be negative. In number 3, it looks like we're going up. We went from negative 20 to negative 10. We went up by 10, but then we went from negative 10 to negative 5, so we only went up by 5. So as soon as I see that the difference is not consistent, then no, this would not be able to be a arithmetic sequence. All right, next, as we look from term to term, again, if you're not sure, you could subtract. Again, I see 13 minus 1. That is a difference of 12, so I want to see if it looks like I am adding 12 forward, and it does. So yes, our common difference here is 12. All right, so what do we want to be able to do next? Well, we know that there are some specific formulas used to describe sequences. This is what we learned at the very beginning of 9.4. There's a recursive formula where your formula is based off of the previous term, and that helps define your sequence. And then there's an explicit formula, and this formula is describing terms based off of the nth term that you are on. And when you have a special sequence, like an arithmetic one, there's actually a special formula that you're going to be able to use. And so this formula will be consistent for every arithmetic sequence that you find. So first, the recursive. There are always 2 parts to your recursive formula. You might remember this from our last bit of notes. You always need to state the first value, the first term in your sequence, that a sub 1, because again, we're basing it off of previous terms, so we need a starter term. Now, our a sub n recursive model, our a sub n, the sequence, is going to equal the previous term, a sub n minus 1, plus the common difference. So let's just remind ourselves what these terms are. So this is previous term, and then plus the d, which is that common difference. So this model you'll always be able to use to define your sequences. Now you're going to want to plug your d in based on the sequence itself, so you're going to plug some numbers in here. The a sub n minus 1 will always be consistent. Now the explicit model. This one is sometimes a little bit harder to understand. I'm going to refer to example 4 just to help us with that. So remember, we want to base our formula off of the n, off of the nth term that we're on. So remember, this negative 35 was 1, this was 2, 3, 4, 5. Now, you could just do what we did in our last set of homework and notes, and that's find the equation that blends the n with the term you're on. However, because this is a special sequence, there is going to be a generic model you can use. So most students will like that because it will be a little bit less thinking. But again, I'm always fine with you trying to come up with your own equation model because at the end it should work. But what I notice is when I want to get to that fifth term, I have added 12, that common difference, on 4 times. If I wanted to get the sixth term, I would have needed to add 12 on 5 times. So here's what you want to do for your explicit model. You want to always take the first term in the sequence. You got to start somewhere. And you're adding on the d n minus 1 times. So like I said, when we were on the 5th term, we needed to add 4 d's on. If we were on the 6th term, we needed to add 5 d's on. So you're adding d on n minus 1 times to that original term in the sequence. So in class, we would have explored this a little bit more, and I usually like to have students kind of come up with and see that on your own. Obviously, via e-learning, I kind of just have to tell you what the formula is. So not as exciting, but again, it's nice to have a model. So what we're going to do in these next 2 examples is use these models and just come up with the equations for the sequences that I've given you. I'm going to have you write out a couple of the first terms for each of these sequences and kind of go from there. So this one's pretty straightforward. The first term is 4, and our common difference, this is an arithmetic sequence, so we can assume we're adding forward by 3 each time. So 4, 7, 10, 13, 16. That would be the first 5 terms. To write a recursive model for this sequence, I would want to state that the a sub 1 was 4, and then I would define the sequence a sub n by saying to take the previous term, a sub n minus 1, and add 3. So again, recursive model, as simple as that for an arithmetic sequence. My explicit model. Now we are basing off of the n, the term that we happen to be on. So I would still need to take the first term 4, and I would be adding 3 on n minus 1 times. So guys, what that essentially means, and I know I didn't ask you this, but if I wanted the 50th term for this particular sequence, and I don't want to write them all out, I would simply use that explicit model and say 4 plus 3 times, and then 50 minus 1. I would have added 3 49 times in order to get to that 50th term. So we could do that real quick in our calculators. 3 times 49, and then add on 4. And the 50th term would have been 151. Kind of nice. Now, one other thing I want to mention about this explicit model. This is not a simplified equation. So I would ask with your explicit models that you always finish and simplify them. So let's look at it in its cleanest state. So we're going to distribute the 3, and then we can combine some like terms. So 3n don't know why that, 3n, and then plus 1 is that final reduced looking explicit model. The one thing a lot of students notice with explicit models is, and arithmetic sequences, is that they're linear. So an arithmetic sequence is like a linear equation, right? So the 3, that common difference, it's like your slope. And then you know, the y-intercept doesn't necessarily mean anything in terms of our sequence itself, but, you know, it just is kind of a cool connection that we can make with previous math that we've done. All right, this next one's a little tricky, and usually in class when students are working on this one in the group, it takes a couple minutes, but they end up figuring this out. Now, it's going to be harder to write the first 5 terms here because I started you on term 4, right? And I didn't give you 2 consecutive terms. You know it's arithmetic, so you do know that you're writing, I'm just going to put a little 4 underneath here so I remember that's the 4th term. We do know there's a common difference from term to term, but we don't have consecutive terms to find that. So we have to be a little creative here. So here's the 4th term. We don't know the 5th. We don't know the 6th, 7th, 8, 9. Now the 10th term was 46. 49. Okay, 46, and that's the 10th term. So remember what's happening. We're adding some d. We're adding some d, adding some d. So from the 4th term to the 10th term, I've added 6 d's. So guys, think about this. You can figure this out. You started at 16. You added 6 differences, 6 d's, and it equaled 46 at the end of that. This equation that you can use here will help you solve for that common difference. So we can simply subtract 46 and 16, which is 30, divide by 6, and that is 5. The common difference must be 5 here. So if I wanted the term that came before the 4th term, before that 16, I would simply be working backwards now, so I would subtract that 5, and it would have been 11. And then I could subtract that 5, it would have been 6. Subtract that 5, it would have been 1. So 1st term, 2nd term, 3rd term, 4th term, and then the 5th term, I can add that 5 forward, and we would have had a 21. So here now is our sequence. Just so you're not confused, I'll get rid of that 4. And we were able to find the common difference d. The recursive model, I would need to state term 1, which is 1 in this case, and then I would explain that the model is taking the previous term a sub n minus 1 and adding 5. My explicit model is a sub n equals the first term of 1, adding on the common difference of 5, n minus 1 times. Now, like I said, we're going to clean that up. We're going to distribute the 5, and we end up with 5n minus 4 for our explicit model. Now remember, we just said that arithmetic sequences are like linear models. The 5, that common difference, was like the slope. Thinking about that, you could have figured out the d maybe a little differently than I did. Remember, I solved it using this equation. But if you want to think of it like slope, you could as well. The 46 and the 16 are like y values, right? What if you did 46 minus 16, and then the 4 and the 10, the terms you're on, those are like the x values. So then you're subtracting the x's on the bottom. This is just like the slope formula. And you get 30 over 6, and you get the same common difference of 5. So however you want to think about a problem that's set up a little different like this, you can. Key connection is we've got linear models. All right, so that is all of the notes for the arithmetic. And just to kind of give a break in the video, I'm going to stop this one here, and then I'll make